always, sometimes never? Is it always, sometimes, and never true that if you have three vectors x, y, and z, that the dot product of x with the sum of y plus z is equal to the dot product of x with y plus the dot product of x with z? Answer is always true, which means that the dot product is actually what we call distributive. So let's prove it. As usual, we'll first let x, y, and z be arbitrary vectors of length n, and we know they must be the same length. If we look at x transpose times y plus z, our first goal will be to add the vectors y and z. And we know we need to do that component-wise, so the first step in our proof will be to write out the components of the two vectors y and z. So the vector y can be written as the column vector with components psi 0 out to psi n minus 1. And the component z can be written as, the vector z can be written as the column vector with components zeta 0 out to zeta n minus 1. By vector addition, the resultant will be a column vector with components psi 0 plus zeta 0 out to psi n minus 1 plus zeta n minus 1. That's just by vector addition. Now what we need to do is to perform the dot product. Here now we have a vector of size n dot producted with another vector of size n. We know in order to do this, what we end up doing is multiplying component-wise and adding. So we'll be adding the product of the chi i's times the corresponding component in the resultant, which would be the psi i's plus the zeta i's, and then adding this from 0 to n minus 1. But these now are just real numbers, and we know that real numbers, for real numbers, multiplication actually distributes over addition. So this is equivalent to the sum from 0 to n minus 1 of the chi i's times psi i's plus chi i's times zeta i's. But this is equivalent to, actually we know if we're summing from 0 to n minus 1, the sum of these two quantities by commutativity of addition, we could rewrite this as the sum I from 0 to n minus 1 of the chi i's, psi i's plus the sum I equals 0 to n minus 1 of the chi i's times the zeta i's. Because addition is commutative on reals. Now, what do we have here? This is just the dot product of x with y. And this is just the dot product of x with z. And so we're done. It's always true that the dot product distributes over vector addition.